Hello, let us continue with our study of Voronoi diagrams. Just I make a quick recapitulation what it is. So once again I import that image. Yes. Okay, so you are given as input a set of points in the Euclidean plane. So these points are called sites. Okay. And I will call these sites as P1, P2, and so on, Pn. So these are the sites, P1, P2, P3, P4. Okay. Now, I want to find out the regions for each site Pi. I want to find out those points that are closest to that site than any other site. So that is called the Voronoi cell of site Pi. This is equal to set of all points. Let's call Q in the two-dimensional plane such that the distance of Pi from Q is less than or equal to the distance of Pj from Q. Okay. For all j not equal to I. This is a convex region because this is essentially the intersection of all the half planes. If I fix a value of j and consider the set of points that are closer to Pi than to Pj, then it's a half plane, and this is each Voronoi cell is the intersection of all half planes Hij. Okay, so it's a convex region, and not necessarily bounded. So this region is bounded, this region is bounded, whereas these convex regions are not bounded. Okay, but if you have any unbounded region, this will have two semi-infinite lines. Okay, for example, the Voronoi cell of this has this and this semi-infinite lines. This one has this and this semi-infinite lines. Okay. Otherwise, if it is a bounded region, it's a convex polygon. Okay. It's either unbounded. If it is bounded, then it is a convex polygon. Now let us say this is the set of sites, we call it S. So by VOR of S, I essentially imply these special things, these boundaries. Okay. For example, I specify this is a finite line This is a finite segment, this is a finite segment, this is a finite segment, and these are semi-infinite lines. So a specification of these corners and along with their connectivity is all that I want to compute when I talk about the Voronoi diagram of a set of sides. Okay. Now, given this definition, I can have a naive algorithm which works as follows. So once again recall that. Let me write in hand. Hij is the set of all points Q such that the distance of Q from Pi is less than equal to distance of Q from Pj. And the Voronoi cell for I is nothing but I or Pi, whatever you call. This is nothing but the intersection of all Hij j not equal to I. Okay. Definitely given Pi and Pj, I can compute the perpendicular bisector between them, and therefore I can define these half planes in constant time. But for each cell, I have to compute this n half planes and compute their intersection. So, at least you are spending something like big omega of n time for each I, Pi. So, this implies that even if I can compute this intersection in big O of n time, this still gives me an algorithm which runs in at least this much time. That is not good. In the last class, we have seen that the size of the Voronoi diagram, that is the number of edges and the number of vertices, these are all linear functions of n, and I simply do not want to make something like n square or even more effort. Okay. So to this effect, today I will introduce a big O n log n time algorithm. This is called Fortune's algorithm. This is named after Stephen J. Fortune. Okay. So, what Fortune's algorithm does is it can detect all these finite intersection points like this. We need to handle the semi-infinite lines a little bit differently. So, let me open another picture to illustrate what I mean by this. I think it is this one. Yes. Okay. So, oops. Okay. So, this picture shows a connection between Voronoi diagram and the convex arc. Okay. So, what I may start with this observation that two Voronoi cells share a semi-infinite finite line if and only if the sides are two consecutive vertices on the convex hull of S. For example, if I consider this 1, 2, 3, 4, 5, 6, 7 sides, then the convex hull is this. Now this corresponds to the perpendicular bisector of this. This corresponds to the perpendicular bisector of this. This corresponds to the perpendicular bisector of this. Likewise, this for this and this one for this. This one for this. Okay. So, given this understanding, I can use something like Preparata-Hong algorithm or Graham scan to compute the convex hull. Okay, this immediately identifies which are my infinite or semi-infinite lines in the Voronoi diagram. Okay, but we have still do not know this finite point. Fortune's algorithm will detect this anyway. Okay. Before going to this Fortune's algorithm, I would like to mention something. That is something like this. Let us. So, one thing is clear that if I specify two ends of a segment in the Voronoi diagram, okay, then this is completely specified. I do not need to have a complete drawing of this line or of the semi-infinite line like this. It suffices to supply only this endpoint and this endpoint. Now, after this convex hull construction, I have determined one end of the semi-infinite lines. Okay. One ends of the semi-infinite lines are discovered by the convex hull computation. Okay. So I assume that the points are in general position. So in particular, no two sides have the same x coordinate, and that will imply this line will be either upward or downward. This is not allowed. A horizontal line is not allowed. Okay. So if that is the case, so for the moment, for an upward semi-infinite line, I say one end is at plus infinity. Whereas for a downward semi-infinite line, one end is at minus infinity. Okay, I will at the last stage put some value at plus infinity. Okay. So I start with, assuming that they are starting from plus infinity and they are starting from minus infinity. Okay. And then I will run Fortune's algorithm. I will detect these finite points here, in a direction from top to bottom. Okay. Actually, in any direction we can do, from left to right, right to left, top to bottom or bottom to top. I will consider bottom to top. Okay. So after we discover all these finite points and how they are connected, we will now do something about this infinity things. Okay. The important thing is that as we gradually proceed, okay, we will discover this point, then this point, then maybe then this point, then this point, something like in this order. Okay. Whereas for the semi-infinite lines, one end is already discovered. So each point, I would say, each segment has 3 states. Let me write these things clearly. One is this, no ends are discovered. Okay. So I will in that case I will say this is a segment yet to open. Okay, or yet to be opened. It is possible that only one end is discovered. So we say that it is now open, and if both ends are discovered, I call that segment closed because I know it completely. Okay. So yet to be opened means, for example, I do not know from where this will start and where this will end, where this will start and where this will end. Note that all the semi-infinite lines are opened. They are not yet closed because I know one end of each. Okay. The other end I have to discover and I have to close. Okay. So, this is how we may start. Okay. Now, this Fortune's algorithm is quite complicated. It is basically a line sweep algorithm. Okay. A line, we will call it a horizontal line. We can take it vertical also, but anyway, let us call it horizontal line. This will sweep from plus infinity to minus infinity. And during the process, several events will happen, which will eventually discover all the segments. Eventually, when this algorithm terminates, we know all the segments and semi-infinite lines are closed. Okay. So this is how this will proceed. This is complicated in the sense that in your line segment intersection problem, we have seen whenever this line, vertical line, passes some point, it can never affect whatever position it has left. With the Fortune algorithm, this is no longer the case. Okay. So, I will open another picture to tell you what I really mean. Okay. Which picture? It's this one. Okay. 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 So, this is my sweep line. Okay. Which keeps on sweeping from up infinity and it will end to bottom infinity. Okay. Now, there is a portion, and this is the eventual, I would say, Voronoi diagram that will be generated. Okay. So, we have already encountered these sites P5, P6, P2, P3, P1, P4. But then, the sites that are below P8 and P7, okay, they will definitely be discovered later. But the point is that they will affect whatever happens, something that happens above the sweep line. Okay. In fact, this picture says that this solid portion of the Voronoi diagram is already generated and this dotted portion is yet to be generated. And they are influenced by P7, P8, the sites that are below the sweep line. So, but there is a portion of the Voronoi diagram which cannot be affected by the sites that are not yet seen. So, this part, the shaded part, is called the ocean or sea. Okay. The part of the Voronoi diagram inside the ocean, that is already finalized. Okay. I will define this ocean soon. And the boundary of the ocean is called the beach line. Okay. Anything above the beach line is the ocean, and we know completely the Voronoi diagram in the ocean. Below, we still have to construct. Okay. So, the sweep line has come here, but still there are some portions of the Voronoi diagram that are yet to be discovered above the sweep line. But there is nothing to be discovered in future above the beach line. Beach line is not actually a line, straight line. I will describe what it exactly means. Okay. So, think of any particular position of the sweep line. Okay. And take any site like P5. Okay. Now, if I consider all points equidistant from P5 and this sweep line, I will have a parabola. This is the focus, this is the directrix. Right. Now, if I consider a site which is not yet seen, okay, it is even more distant, okay, to P5, okay, now let us do this. So, this parabola is the set of all points having equal distance from P5, the focus, and the directrix, which is the sweep line here. Okay. And inside the parabola, that is inside this ocean, the points are closer to P5 than to the sweep line. They are already closer. This point is, for example, closer to P5 than to the sweep line. And if I have any site which is below the sweep line, it will be even further away from P5. Okay. So, the sites below the sweep line do not affect the portion of the Voronoi diagram that lie inside the sea. Okay. That is the reason. Okay. I have this. Now, this is a parabolic arc extending infinitely upward, opening upward. Likewise, for the site P6, I have this parabolic arc. For the site, this is which one? This is P2. This is the parabolic arc. Likewise, for P3, I have this parabola. P1, I have some parabola here, but it is not contributing anything now. For P4, I have this parabola. And if I consider the union of all these parabolas, the inside of these parabolas, this creates my ocean. Okay. And the boundary of the ocean consists of these parabolic arcs corresponding to the different sites. This arc from here to here, this corresponds to P5. From here to here, it corresponds to P6. From here to here, it corresponds to P2. From here to here, it corresponds to P3. And from here to here, it corresponds to P4. Actually, we will see later that I will never maintain this line explicitly. We will only maintain this sequence P5, P6, P2, P3, P4. The sites to which the arcs belong. Okay. And you see that if you walk along this beach line, keeping the sea on your left, your x coordinate will always increase. Okay. It can never decrease. So in that sense, the beach line is called x monotone. Okay. Anyway, whatever it is, in some proofs we possibly require this monotonicity of the beach line, but I will give you an intuitive description of this algorithm without much details. So this terminology is not so important for us. Okay. So I hope you now understand how these parabolic arcs are constructed. Okay, I consider all parabolas. Okay, consider the inside of those parabolas, take the union of this will create my ocean, and the border of this, which is a sequence of parabolic arcs coming from different sides, this sequence is called the beach line, which is x monotone. Okay. Okay, so this is one important observation. P7, P8 cannot be closer to any point inside this parabola than to P5. Okay. So this part is present, but this part is yet to be discovered. Okay. Then you see another very important, I would say, property of this parabola. So look at this point when two parabolic arcs intersect. So on this parabola, the distance between P5 and this point and this, they are the same. At the same time, since P6 this also lies on P6, so distance between P6 to this point and this line, they are same. So if I look at this intersection point, the distance from P5 to this intersection point, distance from P6 to this intersection point, and the distance of this point from this line, these three distances are equal. This means that when the sweep line sweeps down, this intersection point will follow the perpendicular bisector of P5 and P6. P5, P6, this segment. Likewise, if I consider P6 and P2, this is a point, but these two parabolas meet. So, this is equidistant from P6, P2 and line, and this line, sweep line. Therefore, as the sweep line moves downward, this intersection point will actually move along the perpendicular bisector of P2, P6. Okay, here also. P3 and P4, these two parabolas are meeting here. So, this distance, and the vertical perpendicular distance, these three are equal. Therefore, as the sweep line moves downward, this intersection point will move along this P3, P4 perpendicular bisector. Okay. This shows a general situation, what happens. So, this is not an interesting, I would say, position where some event is happening. Okay. So, now let us look at what events are possible and how to handle this. Okay. Okay, maybe there are actually two types of events. One is called a line event, and the other type of event is called site event, and another type of event is called circle event. Okay. Now, the site event changes the beach line, but does not produce any vertex in Voronoi diagram. All vertices are discovered by circle event. Nevertheless, since the beach line is important, I have to handle site events in addition to circle events. Okay, so let me introduce what site event is. Let me first introduce it because it's an easier event. Then we will see what is a circle event. Then we will elaborate how we can handle each of these events. Okay, so I will bring a picture again. Site event, okay, let's make it little smaller, okay, so the idea is that a site event occurs when the sweep line hits a site. In this example, P3. Okay, earlier P3 was before this position of this sweep line. P3 was below it, but then since it is moving downward, at some point it hits P3, and then a circle event occurs. Okay. Now, when a circle event occurs, this introduces a new parabolic arc. At this point, if I look at this focus is P3, directrix is also P3, and directrix is also passing through P3. Therefore, currently this is the degenerate parabola, something like this. Okay. Now, after some, I would say after some more sweep of the sweep line, this will eventually open up like this. Okay. At this point, it's a degenerate parabola. As it moves further down, like from here it comes here, then this parabola actually becomes non-degenerate and opens up. And as you see that, this parabolic arc now breaks this parabolic arc for P1 into two pieces. One here, another here. So this and both this, I would say, P1, P3 and here P3, P1 intersection points will follow the perpendicular bisector of P1, P3. Okay, this is how geometry looks like. Then when P4, I think next one is P4, yeah, when P4 comes, there will be a degenerate parabola coming from here to here, but as the sweep line moves further down, this will become non-degenerate. So P4 will also break the arc for P1 into two pieces. One after P4, one before P4. Okay. So this is as simple as that. So what do we have to do in order to handle a site event? You have a listing of P2, P1 before you encountered P3. Now after you have come across this new site, this list will change to P2, P1, P3, P1. Okay. So let me write down. So earlier the listing on the beach line was P2, P1. After the site is encountered, this will be P2, P1, P3 and again P1. This specification completely describes the beach line. P2, P1, here you see P2, P1, P3, P1. Okay. So the first term corresponds to site 2, second one corresponding to site 1, third one corresponding to site 3, and the fourth one once again corresponding to site 1. Okay. So this is only we have to do when a site event occurs. It just changes the shape of the beach line by introducing a new parabolic arc by cutting one into two pieces. Okay. Now let us look at a circle event. This is a more complicated thing. So now let us look at a circle event. Okay, I will bring a picture again. Okay, circle event, this one, open, this is too big, make it little small. Okay. Okay. Now think of a situation. You have three arcs, maybe PI, PJ, PK. Okay. Here, for example, look at slightly before this event happens. There will be an arc for P2, an arc for P1, then an arc for P3. Okay. Now, when this thing happens, okay, this PJ, the arc corresponding to the site PJ, this vanishes. Okay. PI and PJ grow in order to eat the complete intermediate arc, PJ sitting between them. Okay. Here it is P2, P1, P3. At the moment the arc P1 vanishes, you see that three parabolas are meeting at a particular point. P2, P1, P3. Okay. Since three parabolas are meeting at a particular point, this says that the distance of this point where these three parabolas meet from P2, from P1, from P3, as well as from the sweep line, these four distances are all equal. Okay. This point to this point, this point to this point, this point to this point, and this point to this point. Now, this is a case where this is a point equidistant from three sides. Okay, P2, P1, P3. And therefore, this indicates a corner or a vertex in the Voronoi diagram. And how do I know where this is? The idea is clear. Since these are equidistant from this point, if I draw a circle with this as the center, this circle will pass through P1, P3 and P2. And since the distance of the sweep line is also equal to this, it is the bottommost point of the circle. Okay. So, whenever we have three consecutive arcs, P2, P1, P3, okay, or three consecutive parabolic arcs corresponding to sides P2, P1 and P3, I consider a circle passing through these three sides, okay, and consider the bottommost point of the circle. This is where this event occurs. This is called a circle event, and yeah, so you compute this circle passing through P1, P2, P3 and take the bottommost line, bottommost point. This is exactly when the sweep line, comes to that bottommost point of the circle. This circle event happens. This is called a fork out circle event because this is already open at plus infinity. Okay. Now when you discover that this is going to end, this actually becomes closed. This semi-infinite, which was earlier opened. This now becomes closed because the other end is also known. Its other end is, here, this end is at plus infinity. Now you have discovered its finite end. So this line is now closed. This is called fork out because after this closure, this and this, these two, okay, these two will now be traversed by the intersection of P2, P3, these parabolic arcs, and this will be the intersection of P1, P3 will follow this line. Okay, so this is fork out. Starting from 1, you are getting two different things. How do I detect a fork out case? If I see that this earlier intersection was P2 and P1, it was already semi-open, okay, open at 1, okay, we know one end. Now you have seen its other end, so it has to be closed, and then two new lines or edges in the Voronoi diagram will begin. So one forks out to 2. This is called fork out event. Okay. We have another situation where two arcs may join and subsequently proceed as a single line. So this is called fork in because this forks into only one line segment. So here also what happens, if you look at what happened little earlier than this circle event, so P3, P1, P4, okay, P3, P1, P4. This was, P3 was consecutive with P1, P1 arc was consecutive with P4, but at this point of time, the arc of P3 and P4, arcs for P3 and P4 have become just too big to consume this arc in between. So once again you see that this is a situation where 3 points, 3 parabolas intersect. One for P3, second one for P1, the third one for P4. Okay. So now you see that this distance of this common point of intersection of the 3 parabolas from P3, P1 and P4 are same. They are also same. This distance is also same as the perpendicular distance of this point from the sweep line. So once again, earlier these were consecutive arcs, P3, P1, P4. So if I draw a circle through these 3 sides, its bottom point will trigger this circle event, which in this case is fork in cycle. Okay. So you think a little bit how to distinguish a fork out circle event with a fork in cycle event. It's more or less like this. Fork out means 1 becomes 2, fork in means 2 becomes 1. Subsequently, P3 and P4 will become consecutive, and that intersection point of their, this will go up, and this intersection point will now follow the perpendicular bisector of P3, P4. Okay. So this is basically the geometry. So it's somewhat complicated. There's a lot to visualize, but conceptually it's something like this. Okay. And you see, this circle event marks the end of this and the beginning of this and this, whereas this marks the end of this and this, and the beginning of this. Okay, this way you proceed until you reach somewhere here where other ends are always minus infinity, here, and then when you have generated everything, you have handled all circle events, all site events, you are done. You have generated all points, all finite points, and the semi-finite points, other ends, you already know from the convex hull construction. Okay, so that's basically the algorithm. So once again, let me mention, so how to handle. Okay, so I need to know the position of the sweep line, in particular the positions where events occur. Okay, so I have to keep track of this. So this position triggers events, site or circle, whatever, and I should also maintain the beach line, which is a sequence of sites. Okay, contributing the parabolic arcs. Okay, we do not maintain the parabola itself, parabolic arcs themselves, just something like P3, P2, P1, P2, P4, P2, P5, something like this. This list we will maintain. And also we will have, so beach line, so this list I will call D, this information. So this is a sequence, ordered sequence, something like this. Also I should have an event queue. Okay, so call it E or Q, whatever. I am not using Q today, so I can call it Q. Okay, so this is an event queue. So this B, Q, sweep line I do not need to maintain explicitly. So essentially I will handle trigger by, essentially I will handle the events by looking at the highest y coordinate member of the event queue. Okay, now these events are happening from top to bottom. So queue is ordered from larger y coordinates to smaller y coordinates. Okay, so initially, okay, yeah, so this event queue will store two things. One, future sites that are below the sweep line, and circle events, actually the bottom coordinate of the circle corresponding to three consecutive arcs on the beach line, provided that they belong to three different sites. If I look at this, P3, P2, 1 will store as an event. P2, P1, P2 I will not store because only two sites cannot lead to a circle event. P1, P2, P4 I will store. P2, P4, P2 I will not store because two sites cannot define a circle event. Likewise P4, P2, P5. These things. When the beach line is like this circle event your P3, P2, P1, P1, P2, P4 and P4, P2, P5. These three circle events will be stored. Okay. Now let us see how we can handle a site event and a circle event. Okay. So a site event means I am introducing a new parabolic arc by breaking an already existing arc. So let us say, this is the arc, this is the site event. Let's say we have a situation like this. Okay, and a site is discovered. Let's say this site is Pi. Okay, and let us say this breaks the arc corresponding to site Pj. Okay, and let us say that after this we have, do I need? I think I need. This arc is called Ps, Pt. Okay. So that means earlier we have a situation like this, Ps, Pj, Pt. Okay, so this is before the site event. After the site event occurs, I have situation like this, Ps, Pj, this is broken in two parts, Pj, Pt. Okay. So now what happens? Earlier these 3 points were adjacent. These 3 arcs were adjacent. So Q contained the circle event for this triple. But after this Pi is introduced, Ps, Pj and Pt, so they are no longer adjacent. Okay. Now you see there are 3 adjacent things, Ps, Pj, Pi, Pj, Pi, Pj and Pi, Pj, Pt. Okay. So, but Pj, Pi, Pj, this triple cannot constitute a circle event because they belong to only 2 sides. But Ps, Pj, Pi will, Pi, Pj, Pt will. So, what you have to do, after this insertion, you remove this circle events corresponding to Ps, Pj, Pt, this triple. Instead, after removing this, you insert the circle events, this one and this one. The circle event correspond to these triples. So remove from Q, insert in Q. The circle events corresponding to this triple and this triple. Okay, so this is how handle a site event. Okay, now what about a circle event? Handle a circle event. So what triggers a circle event? When a parabolic arc corresponding to, let's say, Pi and a parabolic arc Pk, and you have Pj here, this is actually consumed by the growing arcs Pi and Pk. Okay. So this will vanish. This vanishes. Okay, Pi and Pk consume this. Okay, so once again I assume that there is a parabolic arc before that, Ps, and something after that. If there is no such thing, you don't have to worry about this. Okay, so this is before. Now after a circle event occurs, when a circle event occurs, this simply vanishes from the bitch line and the list changes to Ps, Pi, Pk, Pt. Okay. So earlier I had stored the circle event corresponding to Sij in the event queue. I also have the circle event Ijk in the event queue, and I had Jkt in the event queue. Now since this event is handled, the circle event corresponding to Pi, Pj, Pk will anyway be removed. Okay, because after you handle an event, you simply remove it from the queue. But you have to consider this Ps, Pi, Pj. So this and this remove from queue, and this is anyway automatically removed by the event handler. Okay. Moreover, now I have two new things. Ps, Pi, Pk, this triple have now become consecutive. Pi, Pk, Pt, this triple have now become consecutive. So, now add to queue the circle events for these pairs or triples. Okay. And this is what I am saying, what you are doing in Q and the bitch line B. At the same time, you have to find out whether it's a fork in or fork out circle event. Based upon that, you close or open some edge of the Voronoi diagram. This part I am not discussing. I am just telling how this event Q and the bitch line are modified by the circle event. Okay. So this is basically what is done. But you see that both here site event and circle event, you need to make arbitrary deletions from Q or addition to Q. Okay. Arbitrary. Insert, delete. Okay. Insert is not that a problem even if you use max priority queue. Okay. But deletion is a problem because it's an arbitrary deletion. Okay. And you also make delete max, maximum y coordinate event you are deleting. But since you have to, your queue has to support arbitrary deletion, it is preferable that you store both and also you see that this insertion is also at an arbitrary point. Okay. It can be anywhere. Okay. So that means implement both the bitch line and the event queue as height balanced BSTs. Okay, like AVL trees. So that each insertion, deletion, find min, find max, all these things can be done in Pgo of log size time. But size is the size of B or size of Q. So now let us see what the size is. Okay, so the first event happens when the sweep line encounters the topmost side. So now, if the topmost size is called P1, at this point we have one parabolic arc. Okay. After that, each side event increases the number of arcs by 2. Okay. For example, P1 is broken down into P1, P1 and P2 is inserted between them. Okay. And there can be at most n side events. Okay. So the maximum size of Q is therefore Q, not Q, which line? Q is, okay, which line? Maximum size of B is therefore 2n minus 1. Okay. And it's also important to see that a circle event removes one arc from B. Whatever it is, this 2n minus 1 is an absolute upper bound. Okay. So 1 plus 2 plus 2 plus 2n minus 1 times, this is 2n minus 1. And if in between some circle events happen, the size of the pitch line may reduce, but this is the absolute maximum. Okay. More importantly, this also says that maximum size of Q is, it can store n side events, and if the pitch line is of this size, 3 consecutive things will give one circle event, and there are 2n minus 1 arcs, so you cannot have more than 2n minus 3 circle events, okay, at any point of time. Therefore, the number of maximum possible elements that the event Q can store is 3n minus 3. So this is big O of n, this is big O of n, big theta of n, big O of n, big O of n, and therefore these are all big O of log n. Okay. So we are handling how many? Okay. So the event size cannot be greater than this. Okay. And we have seen that the size of is linear in n, right? We have seen it, which essentially implies that although there may be multiple removals and additions of circle events, each circle event discovers one end of an edge in the Voronoi diagram. That means, so big O of n circle events will happen throughout the journey of the sweep line. Likewise, there are only n sides, so y big O of n, just n. In the total journey, we will have n side events. Okay. And if you maintain a balanced binary search tree, because the height is always big O of log n, you see that this algorithm runs in big O of n log n time. Of course, there are some other issues involved, like how to maintain these edges in the Voronoi diagram. There is a specialized data structure for this. You will not study much about it, but let me just mention. Doubly connected edge list, DCEL. Okay. But anyway, let us not worry too much about this data structure for storing the Voronoi diagram. Okay. Anyway, it can be handled in appropriate time, and overall running time is therefore big O of n log n. Okay, that's more or less about this algorithm, but as I mentioned, there is still one more thing to do. That is, somehow I have to define or redefine that plus infinity and minus infinity that I set here. Where? Let me see. Okay, this is the naive algorithm. Yeah. This plus infinity and minus infinity, this should now be made more precise. Okay. But this process is fairly straightforward. I will again open a picture to illustrate this one. Yeah. Okay. So what happened earlier, we assumed that this originates from infinity, plus infinity, plus infinity, plus infinity, and this is going to minus infinity, minus infinity, minus infinity. Okay. But after this, I have run Fortune's algorithm and discovered this, everything, all the finite points. Okay. So now what I do, I just take a bounding box big enough to enclose all these finite points, okay, and all the sides. Okay. So take a bounding box large enough to contain all the sides and all the vertices of vertices, of course, means the finite vertices discovered by the Fortune algorithm. Okay. Then what do? You know the semi-infinite lines correspond to the perpendicular bisectors of the adjacent points, adjacent vertices of the convex hull. You already have this convex hull, right? So now you just do this thing. Consider this and this two adjacent points on the convex hull. Generate this perpendicular bisector and then figure out where exactly this perpendicular bisector meets the bounding box. This bounding box need not be square, need not be a rectangle. It may also be a circle. Okay, some region which is big enough to contain this entire finite part. Okay. So now I may replace this plus infinity by this. Okay. With the understanding that this will go further, but anyway I will look into this finite snapshot of the Voronoi diagram. Likewise, take the perpendicular bisector, see where it intersects the bounding box, and replace this plus infinities by this and minus infinities by this. This is the lower hull, minus infinities, upper hull, plus infinities. Okay. So that now completely specifies the Voronoi diagram. Okay. This I am just bounding with the understanding that this will go up to infinity. This will also go up to infinity. But I am just looking at this finite area where which is the important area, I mean. Yeah, something like this. Okay, so that's certainly a complex algorithm. There is a lot to visualize. Moreover, certain things are kept slightly vague, like how to handle these edges. Anyway, this still gives you a brief introduction or exposition to an algorithm, a good algorithm, n log n time algorithm for computing Voronoi diagrams. So with this, I stop this section on geometric algorithms. Next time we will start the theory of NP completeness. Okay, so see you until then. Bye.